Are you ready for a surprise? Now, think back to your trigonometry class, learning the unit circle, memorizing the values of your trig functions, memorizing trig identities. Well, you are familiar with unit circle trigonometry, but did you know that there's a branch of trigonometry based on a unit hyperbola? This is called hyperbolic trigonometry. And believe it or not, you already have some experience with hyperbolic trigonometry in this class. I just didn't tell you that's what we were doing. So let's look at our two diagrams here. Unit circle trigonometry is based on a circle of radius 1. The equation of that circle is x squared plus y squared equals 1. Now, we can calculate the ordered pairs of every single point on this unit circle using our traditional trig functions, right? The x coordinate is given by cosine, the y coordinate is given by sine. Now, instead of looking at a unit circle, if we look at a unit hyperbola, the equation of our unit hyperbola is here. Notice the distance from the center to this vertex is 1, and from the origin or the center of that hyperbola to this vertex is also 1. We can locate ordered pairs of every single point on this hyperbola using our hyperbolic trig functions. That is, the x value of each ordered pair is given by hyperbolic cosine, which we abbreviate COSH of t, and the y coordinate of each point on that unit hyperbola is given by hyperbolic sine of t, and we denote that SINH of t. Now, believe it or not, just like with unit circle trigonometry, there are identities or equations expressing relationships between our hyperbolic trig functions. Now, these hyperbolic trig functions can also be defined in terms of natural exponential functions. So these 6 formulas that you see here are the definitions of our 6 hyperbolic trig functions in terms of the natural exponential function. So hyperbolic cosine of x, when I see the COSH, I read it hyperbolic cosine of x is equal to e to the x plus e to the negative x over 2. Whereas hyperbolic sine of x is equal to e to the x minus e to the negative x over 2. So notice the cosine has the positive in between, sine has the negative in between. That's a pattern that happens a lot. Now, here's how I remember which one's positive and which one's negative. Cosine is positive, sine is negative. Why is sine negative? Well, in sine, I can see sin, and sin is bad. It is negative, right? So cosine goes with positive, sine goes with negative. We see that in the double angle identities as well. Now, examine hyperbolic tangent of x. Hyperbolic tangent is e to the x minus e to the negative x over e to the x plus e to the negative x. Go back to ordinary unit circle trigonometry for a minute. We know that ordinary tangent of x is sine of x over cosine of x. Well, what happens if I take hyperbolic sine of x and I divide it by hyperbolic cosine of x? So this one over that one, right? I hope you recognize the denominators would cancel and we would end up with hyperbolic tangent of x. So this relationship between ordinary tangent of x, sine and cosine of x, is very similar to the relationship between hyperbolic tangent of x, hyperbolic sine of x, and hyperbolic cosine of x. Also, look at the relationship between hyperbolic cosine and hyperbolic secant. If you had to express the relationship between those two functions, what would you say? Hopefully you recognize, oh, they are reciprocal functions. So 1 over hyperbolic cosine is equal to hyperbolic secant. Now, we know that as well. Let's write it this way. Ordinary secant is 1 over cosine of x. In addition, hyperbolic secant of x is equal to 1 over hyperbolic cosine of x. Now, not every single unit circle identity has its counterpart in hyperbolic trigonometry, but you can certainly see that there are going to be a whole new set of identities associated with hyperbolic trigonometry. Now, to get a feel for how these work, let's attempt to evaluate hyperbolic sine of natural log of 2. So to evaluate a hyperbolic sine function, I'm going to use its equivalent natural exponential function. So hyperbolic sine of x is equal to e to the x, remember this is the one that has the negative in between, minus e to the negative x over 2. So hyperbolic sine of the argument natural log of 2 is going to be e to the natural log of 2. I'm just plugging natural log of 2 in for x, all divided by 2. Now, if we have the pattern e to the natural log of x, that's our inverse relationship. We're going to get x. So e to the natural log of 2 is 2. Now, e to the negative natural log of 2 is not quite so simple. We have to first move that coefficient up into the exponent position before I can apply that inverse relationship. So once we move that exponent, then we can evaluate this to be 2 to the negative 1 or 1/2. 2 minus 1/2 gives me 3/2. I'm just going to simplify this by multiplying the top and the bottom by 2. So we end up with 3/4. So hyperbolic sine of natural log of 2 equals 3/4. So congratulations, you just evaluated your first hyperbolic trig function. Now I have to admit I have snuck some of these problems in already. If you'll go back in your notes a little bit, go back up to, I'm going to start with, oh, there it is. Example C from the previous section. Example C. Notice the pattern there, e to the x minus e to the negative x over e to the x plus e to the negative x. What we're dealing with there is none other than the integral of hyperbolic tangent of x. It's just written in terms of its natural exponential functions. And just like the integral of ordinary tangent of x involves natural log of the absolute value of secant, we have a form of that here in our answer as well. So if you look at example 5, the differential equation that we solved, notice our derivative here. Our derivative is the natural exponential form of hyperbolic cosine of x. And notice what we have in our result. This is the exponential form of hyperbolic sine of x. So what we can learn from example 5 is that the derivative of hyperbolic sine of x equals hyperbolic cosine of x. Now think about it. The derivative of ordinary sine of x is ordinary cosine of x. So even the derivative and integral relationships between our hyperbolic trig functions will be not exactly the same as, but similar to our ordinary trig functions. So let's try a derivative of one of these guys. We want to show that the derivative with respect to x of hyperbolic tangent of x is equal to hyperbolic secant squared of x. So you can say, in a sense, we're proving an identity here that involves a derivative. So to differentiate hyperbolic tangent of x, we're going to replace it with its natural exponential definition. So the derivative with respect to x of hyperbolic tangent of x is going to come from this equation right here. So we're going to differentiate this, but before we differentiate, we're going to replace hyperbolic tangent with its definition in natural exponentials. So we need to find the derivative with respect to x of e to the x minus e to the negative x divided by e to the x plus e to the negative x. So to differentiate this function, we're going to, of course, need our quotient rule. Notice I am executing the derivative, so I'm dropping the differential operator. The differential operator is a pending operation. As soon as I carry out that operation, I drop that d over dx. So I'm going to start by squaring the denominator, and that helps me to remember that's the factor that I lead with in the numerator for the quotient rule. Then I multiply by the derivative of the numerator. We're going to get e to the x minus e to the negative x times negative 1 using our chain rule, which will simplify to plus e to the negative x, minus the derivative of the denominator, that's e to the x, minus e to the negative x. Remember, that's a copy of the e to the negative x, times the derivative of the exponent, which is negative 1, times our numerator e to the x minus e to the negative x. Now, the only way around this problem is FOIL. There's nothing that's in common between our two terms that we could factor out, so we are going to need to FOIL our two sets of binomials. So applying FOIL, the product of our first two terms, e to the x times e to the x, is e to the 2x. Remember, when you're multiplying like bases, you add the exponents. Then the product of our outside terms, e to the x times e to the negative x, when we're multiplying like bases, we add the exponents, right? We're going to get the same thing for our inside terms, and for our last two terms, add those exponents to get e to the negative 2x, okay? Now we're going to subtract the FOIL resulting from the next two binomials. However, because we're subtracting, we want to make sure we distribute that negative throughout the product. So I'm going to use a set of parentheses here. Okay, the product of our first two terms, e to the x times e to the x, is e to the 2x. Outside terms, we have negative e to the 0th power. Inside terms, negative e to the 0th power. Again, I'm just adding the exponents, plus e to the negative 2x. All divided by e to the x plus e to the negative x squared. Let's begin to simplify this. Now remember, when we have e to the 0th, that's equal to 1, and we've got lots of these e to the 0ths here. We're going to replace those with 1s and combine like terms. Also notice here I have e to the 2x minus e to the 2x. Those are going to cancel. Also, I have e to the negative 2x, don't forget to distribute your negative here, minus e to the negative 2x. Those are also going to cancel. So our numerator will end up being 1 plus 1. Now don't forget this, minus negative 1 minus 1. Let me write it out so you can see what I'm doing here. Those are the leftovers in the numerator, right? So we have 2 minus negative 2, or continuing over here on the right, 2 minus negative 2 is 4. Okay, so we've differentiated, we have simplified. Remember, we were trying to prove this relationship here. So we have the derivative of hyperbolic tangent on the left. We're trying to arrive at hyperbolic secant squared. So notice I could rewrite this as 2 over e to the x plus e to the negative x squared, right? Then if we look at the definition of hyperbolic secant, we have a 2 on the top, e to the x plus e to the negative x on the bottom, which matches what we have right here. So this is equivalent to hyperbolic secant squared. Don't forget your h in expressing those hyperbolic trigonometric functions. So just like the derivative with respect to x of ordinary tangent of x is equal to secant squared of x, you can now see the derivative with respect to x of hyperbolic tangent of x is equal to hyperbolic secant squared of x. So in addition to a whole new set of identities, you also have a whole new set of derivative relationships. One thing I do want to point out about hyperbolic trig functions that's a little different than your ordinary trig functions. Think about the derivative of ordinary cosine of x. Hopefully you recognize that's negative sine of x. However, when we differentiate hyperbolic cosine of x, we get positive hyperbolic sine of x. So in that respect, it's a little easier to remember the derivatives of your hyperbolic trig functions. The derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. You don't have to strain your brain to remember which one gets the negative. So I hope you find that interesting. If you're curious and you want more information, I recommend looking this up on the internet and finding out more about hyperbolic trigonometry. As far as our purposes, you do not need to memorize these formulas. I just want you to be aware that they exist. You can refer to them in your notes when you need those formulas, but also notice when you come into contact with combinations of exponential functions, you may be dealing with a hyperbolic trigonometric function.